Hello again. Today we are going to make some progress with our fitting capabilities. I will show you how we can do a systematic analysis of many measurements that you have done on a series of samples. In this case, it's a very simple example where people have recorded reflectance spectra of silver layers deposited on microscope slides. With the purpose to find out the deposition rate. They deposited several samples with evaporation times of 1 second, 2 seconds, 3 seconds, and so on, up to 22 seconds. And the purpose of the fit is to find out the layer thickness, the silver layer thickness for each sample, and then get in the end the deposition rate of this process. I will use this example, well, because I have the data recorded many years ago, and because it's very typical and very simple. So I can start with code when you start it up like this, and we will develop again a user interface. But since I have another session with user interface explanations, I will do this rather quickly. So let's go to full screen mode, press F7 to go to the tree view, open the list of view elements, delete them all, and then start the work on the optical constant database, where we will pick two materials, microscope slide glass, which is in the section here starting with G. That's this one. I will not check the substrate in this session. I have made a separate video about that. So let's assume that we have done the substrate characterization carefully and correct. So we can use the microscope slide glass here, and it's a 1 millimeter glass, which has been used for these experiments. For the silver, I use the silver model, the AG model TL item of my database, which I use very often. And once we have the materials here in the list, right mouse click there, we can go to the layer stack, define a thick layer, which is 1 millimeter of microscope slide glass, and on top of this, let's define a thin film of silver. So that's the model actually, and now we can define the spectrum. Actually, the data have been measured from 200 nanometers to 1,000 nanometers, as far as I remember, or 1,100. Let's do the analysis from 300 to 1,000 nanometers with, let's say, 200 points. That should be enough. And then let's adjust the graphics here. Graphics, edit plot parameters. We want to see the graph from 300 to 1,000 with 100 nanometer steps from 0 to 100. Okay. So let's see where we can get the measurements that we have to analyze. So before we do a batch fitting, we have to make a fit routine that really works for all kinds of layers that are deposited. So we have to go to the thin ones, to the thick ones, and make sure that the model works. So let's import one of the test spectra right now and set up the fitting routine. So we import from File, and in the code folder that you have when you install code, there is a folder called Scout Tutorial 1, and in that folder there are 22 spectra called AG1 up to AG22. Let's start with one in the middle, AG 12, for example, and these are stored in a so-called standard format, Scout standard format, and so that's what we have to use to read the data. When you read them, you get the information about the spectral range. Wave numbers here is not correct. These are all in nanometers. Okay, now we have the measured data here in red. Let's now select the fit parameters. Actually, for the beginning, there will be only one, namely the thickness of the silver layer. So we will go to the list of fit parameters, select with plus the thickness of the silver layer, which is here. And then let's go to the, well, okay, now we have to make the user interface. I will do it very simply, defining just the spectrum and the list of fit parameters and the layer stack in the main view, which is easily to be done like this. We open the list of view elements. It's empty because we deleted all of them. We drag the spectrum that we want to see, the layer stack that we want to see, and the list of fit parameters. Then we can press F7, move the spectrum to the right, and have the fit parameters here and the layer stack here. Okay, later on I will need some more space, so I will leave this open. So we will have the spectrum only here in the upper right corner. I will make it even a little bit smaller. So let's define boundaries for the silver thickness. The bottom boundary should be 0. The top one can be, let's say, 100. And as you can see, 100 is too much for this, at least. We can check it manually. This would be something which is correct. So we can fit, press the start, we can fit this automatically. Very nice fit. Seems to work almost perfectly. So we are lucky with this model. Let's load one more spectrum and check if our fitting works also. Let's take AG number 6. That means 6 seconds deposition time. Okay, that seems also to work, except for this region here. I will make some remarks about that later on, and let's finally test one of the thick ones, or the thickest one actually, and press start, and the fit goes up like this. So that seems to work nicely. So let's now do the fit for all the samples and collect the results in a table. That's the purpose of what I have called the batch control window. And in the tree view, you will find an item below the workbook, which is called batch control. If you double click that, you have basically a spreadsheet here. And what we can do is now use the command in the batch control window, which is called prepare new batch fit. And this will prepare the batch fit for us. Actually, it will prepare 3 pages. One is called results. That will collect the results for all samples that we are investigating. Then there is a page called input options, where we can set basically the path for the spectra, so that code can find the spectra. And then there's a page called prefit, which we can use to tell code to use certain prefit sets. That means sets of parameter values that it should check before the actual fit will start. Actually, we will not use the prefit in today's example, but we will use the results page and the input options. So now let's add let's add all the measured data here. We have to do it like this. Here in this results, on the results page in the first column, you have basically a section about the sample where we will have names here, and we can have a line with parameters. Then there is a section about spectra that belong to these samples, and here there's only one spectrum, one reflectance spectrum in our oh, well, sorry, I have to go back. I have to check. In the case of reflectance, if I did everything correct, and for the spectrum here, it should be 8 degrees, and let's be super correct, mixed polarization, and everything else is okay. Sorry about this interruption. Let's go back to the batch control. The spectrum R here should get some input spectra names. The names will be collected here. And then when the fit runs, it will fill out some more lines here, more rows, about the progress of the fit. It will write down the fit deviation for each sample, and that's the most important part, the obtained thickness values. That is this column here, or this row here, sorry, which is the thickness. Okay, let's place the cursor in the row where the reflectance spectrum is and use the command. Actually, I will not explain all the commands here, just the commands that we need for today's work. So there's a command which is quite powerful and useful now, which is called actions add multiple files, which will allow us to select many files in one step. Here are the files that we have loaded partially before. I will select the last one with the cursor and then hold the shift key down and select the first one. That makes Windows to select all these in the right sequence. Then we click on open and update here this list by clicking somewhere. And so now we have all the files here, and that's not all actually. There's one thing we have to check in input options. In input options, you find a row called spectrum, and this gives the name of the spectrum object, and then a row called path, or a column called path. And that is the path of the data. That is correct. That was filled in automatically for us. The input format, that is not filled in correctly for us. That's the input format. That's basically the file format, and the standard format that we have here is number 1. Actually, you can count those formats if you click on import here, and you get the file selection dialog. You can count from the top here. Scout standard format is number 1, XY format is number 2, Spectra calc format number 4, and so on. So you can count the index from the top, and right now we are reading Spectra in this file format, which is called Scout standard format. Okay, so now this is correct. Input option we don't need. These things are also not relevant at the moment, so that should be okay. Let's do the first test here. Let's go to column number 10, which is this one here, and just test if everything works correctly. And we can do that. Should always be the first test if we can do the fit automatically for one selected sample. And there's a command called fit current sample, which we can use here. If we click on that, you should see that code loads the spectrum, does the fit, and writes down the results. We can verify that here, and let's check for sample 13 if that works again. Fit current sample, F7 to go back. Obviously that seems to work. Okay, when this works, the only thing that remains to be done now is press go, which will do the batch fit for all the samples. It will be rather quick, and we can watch it in real time. Let's just press go and watch what happens. So all the data are loaded, then the thickness is fitted, and hopefully the results are stored. And then it's finished. Actually, it makes sense to open the status bar with the keyboard command S. That's the status bar here. So we would see the progress of the fit. Actually, we can have the batch fit once more. To see that, I press go here, and you can see here the fit deviation, a so-called rating, which is in most cases good. And then you can see here some information about the progress of the fit concerning the time that it needs and the number of iterations for the optimization routine. And okay, that's done already. So let's inspect the table. I should resize this column a little bit. Well, here are the thickness values of 0 initially, which is probably not correct. After 4 seconds, there should be some silver, but nevertheless, the fit result here is 0. So we will have to take a closer look at the individual fits. There is a tedious way how to do it, which is selecting a sample. Let's say let's pick number 4, which has the strange result of 0 for the thickness. And you can use this shortcut command here, this little button. That means send the fit parameters and the spectra to Scout. Actually, in this case, it's code, but these buttons here are labeled for the Scout software, which is similar to code. If we click on that, for this column, the spectra are loaded and the results for the fit parameters are loaded. So if we press F7, we see now here the model for this sample. And obviously the fit is not very good. And let's watch it in a different way. If we would do that here for all the 22 samples, that would be rather tedious. Select a column, click on this command, press F7, press F7 again, go to the next, and so on. Luckily, there's a shortcut, and this is called Actions, a loop through results. If we click that, code will load the results for the first fit. Then it will give us the option to select the next sample, the next one, and the next one, and so on. So we can go through all the results and watch the fit quality here, and go and check if everything went correctly. Obviously, for the initial fits, I will execute this command again, actions loop through results. Here, the fits are not very good initially. For sample 1, sample 2, sample 3 is even worse. Sample 4. Here, actually, I have the impression the fit could be nicer. So maybe we have to improve the fit a little bit. Okay, we can do that. We have to do that anyway. So we can do that now. So let's improve the fit. Let's first continue to visualize some of the results in a more useful way, and then we will improve the fit and watch if we could make some progress. It would be good to see all the thickness values in a graph, and there's a view object that can do that. Before we generate this view object, it makes sense to actually to set the parameters here. Usually those names for samples can be text. Here these are just names which are numbers actually, and we can make a copy of that by selecting the first cell here, then select to the right, and then press copy and copy to clipboard, and then we go to the next cell where we can have for each sample a parameter value like a temperature, or in this case a sputtering time, and then we can paste the numbers here. So actually these could be names, but these should be numbers. The parameters here should always be numbers, so it's good to have clear numbers in this row. And it starts with cell B3. That's the first number, and the first thickness is in B15. So now we can generate the view object. Let's go to the list of view elements and generate a new object of type batch control graph rows. That will show data, display data in a graph that we have stored in rows in the batch control window on the results page. So if we generate an object like this, we could call it thickness versus time, and then we can edit this object, and it will first ask us the range of the x values. I remember that it starts with B3. I think it ends with W3, but I'm not sure. But we have to correct. Maybe we have to correct it. Maybe not. That should be the last x value, and then it will ask for the range of y values. First thickness was B15, and then consequently the last one should be W15. Now we will get a graphics dialog for the graph, and actually we can give it a title: thickness versus sputtering time, and the frame mode should be 3. That gives us some grid lines. Grid line mode should be 1. They should be kind of gray. And okay, this is the sputtering time. In seconds. And this goes from 1 to, let's generate the display from 1 to 23. Then we have the beginning and the end. In steps of 5, no decimals, and the thickness values, they have been in nanometers, and they last from 0 to, I think, something like 28, but we can go to 30 with steps of 5 and no decimals at all. That should be okay. And if we click F7, we should see the results, which is not too bad. It's almost a straight line, except for the problems that we have here initially. Let's put it to the side. Actually, it would be nicer to see the individual points. At least I find it nicer. So I can click Control, which opens the dialogues again, and the style of the line is given by line mode. If we put 16 here, we have little dots which show all the points that we have investigated. Okay, let's generate another graph, and which is the graph of the fit deviation, so that we can see which are the fits which work nicely. They will have a low fit deviation, and which are the fits that generate a problem. So let's do this once more. But let's first look up in the batch control window where we have the fit deviations. These are the numbers 0.02, 29, 0.01, 1.0.01. That's the biggest number, I guess. And these are in row number 10. So now we can display the fit deviations in the view also by basically we can duplicate this command here. We can duplicate this object, sorry, and we can call this fit deviation versus sputtering time or versus time. This is the same X range. Now we have cell B10 to W10. And now we can call this fit deviation versus sputtering time. And the sputtering time axis is the same, but the fit deviation needs some more care. Fit deviation, and this has no unit. And now we can use actually a unit factor. Let's practice that. We can call this 1e minus 7, I guess. That would be a nice small number. And then we go from 0 to 10,000 as far as I see. No, 100,000 in steps of 10,000. Okay, that's the fit deviation, and I hope I did everything correctly. So we can now see a graph like this. Actually, the biggest one here is even higher. So I have to go to, I guess, to 120,000. Yeah. So now we see, okay, the first 4 fits are really bad, and the others are okay. They have a very, very small fit deviation compared to the first. So let's now improve the fit. I have lost here the graph of the reflectance spectrum. I guess, yeah, it has lost its source. I don't know why, but we can assign the reflectance once more. That is strange. Probably a bug in the software that I have to find and remove. Let's see if we can see everything again. Yes. Actually, it would make sense to store this for the first time before I do something wrong. File save as. Let's store this somewhere where I can find it back. Transfer. There should be a folder called video, batch fit, AG on glass, batch fit, step 1. Okay, that would be the first secured configuration. Let's improve the fit a little bit, and we will improve that even more in the next step. I would like to show you a systematic search for the thickness. Right now, if we do the batch fitting, the program just starts at the current value, and then it runs the downhill simplex algorithm. So if I press start here with this thickness and I press start, then the program does some small steps, and it tries to fit this spectrum. Sometimes that's okay if we are close to the best value. Doing small steps, starting from there, is okay. But in most cases, it's nicer to have a solution which is independent of the current value, because if something goes wrong with one of the fits, you will never find back to good values if you always start with a very wrong value, somewhere far away from all the good solutions. So let's go to the list of fit parameters here and take a look at the column variation. Let's say there's the current value, the name of the fit parameter, and this variation, which is usually downhill simplex. There are some more settings, and you can cycle through all the settings with the function key F4. If you press F4, there's an empty cell. If you press it again, there's the item grid 10 points, grid 20, 50, 100, and so on. There are several settings, and when you are cycling through, you finally arrive at downhill simplex again. With F5, you cycle backwards. With F4, you cycle forward in this list. Okay, so let's go to the options of variation, which are called grid. There's one called grid 50, and we can practice with that. Grid 50 points means before anything else is done, code will divide this interval here from 0 to 100 in 49 intervals, and it will then check all the values from 0 to 100 using 50 points with equal spacing in between, and then it will take the best one of these points, and then it will do a downhill simplex starting from there. So we are doing a systematic scanning of this whole range, like we would do, let's say, like we would do by hand. If we start here and we are watching the fit and taking a look at the fit deviations and remembering, okay, the lowest one was somewhere here, and then we start the fit. So in this case, we find the best value starting from here somewhere, and that is done automatically if you use this option with 50 points on the grid. So we can just check if this new method also works, or even works better as before. If I press go in the batch control, all the batch fittings are done again. So now you can see that the fit deviation here for the bad fits are somewhat smaller, at least for numbers 3 and 4, which were really bad. They are now a little bit smaller. The thickness values look a little bit more reasonable. Still, the fit deviation here is larger, as for large thickness values. So let's just explain that. We can use the command actions loop through results again. And what happens here at the beginning is if you do sputtering for 1 second of silver on glass, actually the spectrum, the red one here, the measured one, looks very different from the blue one. It has a structure even here, a little mountain, which is completely missing in the blue spectrum, in the simulated spectrum. And the reason is that there is no continuous silver film when the growing starts. It's a film of islands which are separated from each other, and they have very strange optical properties, very different from homogeneous continuous silver layers. And so this happens in the first seconds. So for 2 seconds there is still the structure. It's getting weaker and it moves to higher frequencies or smaller wavelengths. At 4 there is a little bit left here of this bump, but it already looks a little bit like we get from the simulation. And finally at 5 seconds, the model that assumes a continuous homogeneous silver film works already quite nicely, except for this range here. And starting at 6, this never really works good until we reach very high values here. Now it's gone. This has something to do with surface roughness, and we will just neglect it here. But obviously, initially, when we have silver islands, our model is not very good. Nevertheless, here the thickness values, well, they somehow fit in this row, but we shouldn't use them to get the sputtering rate. We should only use those here, which are more or less on a straight line. Good. Okay. Let's take a closer look at the fit deviations. We can stop this here, and we can click on. We can hold the control key down, and now zoom in a little bit. We can go from 0 to, let's say, 10,000 in steps of thousands, or we can go even from 0. We can ignore the big ones and just can go from 0 to 1,000 in steps of 100. So we can see the fit deviations here, and most of the fits look good, but here they are not. Well, there are still some differences. Yeah, actually, I would like to show you a small improvement that we can do. Actually, what happens with silver layers is that the optical constants are thickness dependent. I have made a video tutorial about the optical modeling of conductive thin layers, and you can listen to that, or you can watch that in order to learn more about this. But here I just want to tell you that the damping of the electrons will depend on the thickness of the silver layer. Basically, the quality or the mobility of the electrons in the silver layer will be depending on the thickness, in the sense that for thin films the mobility should be low. There are many defects, and if you produce thicker layers, then the density of defects will be lower. At least that's what I would expect. So we can improve the model a little bit by giving the silver the thickness dependent property, and actually the only thing that we have to do is we have to select the damping constant of the electrons in the silver model as an additional fit parameter, so that our model has the chance to adapt itself to different mobilities of the electrons in the various silver layers that we have produced. So let's go to the list of fit parameters, and let's add one, and we can identify the silver model here. There's a Drude model for free electrons, and actually it has this damping constant, and this is the only thing that I would like to change from layer to layer. We can give it a range from 100 to 1000, which is a range of typical values. 100 would be very, very good silver, 1000 very bad. So the truth should be in between. So let's now do a systematic search as well for the damping constant of silver. Or actually, what we could do first, maybe I should show you some more options here. In this variation column, we can cycle through all the options and stop at a setting which is called start at low limit. The next one is start at interval center, and the next one would be start at high limit. And I would like to go back with F5 to the setting start at interval center, and in this case code will start with the value 550, which is in the middle of 100 and 1000, and it will use this as a starting value, and then for every fit, and then do the downhill simplex starting from there. So let's see what we get if we do that. Let's go to the batch control window, press go, and let's now watch the fit, and also watch basically the thickness deviations if they get smaller. Some of the values get smaller, some don't. Well, some are just staying. So it's not a huge progress, just a little progress. Yeah, some of the points have been smaller. Okay, let's take a look at the obtained damping constants. Actually, we have to make a little bit of space for that. We can push this to the side, make this a little bit smaller. Okay, like this, and a little bit bigger, like that. Okay, and generate one more of these graphs, and let's duplicate the thickness versus time and call this damping versus time. Damping versus time, okay. We have to edit this one. X-axis is the same. This should be now row number 16. We have now one fit parameter more. And this is now electron damping versus time. And let's say we can have values from 100, or let's start at 0 to 1000. Let's use a spacing. Oh, sorry, that was completely wrong. These were the thickness value, the sputtering time. Sorry. Here, that's the damping constant of the Trude model. This is measured in 1/centimeters. Okay, and we should have values between 0 and 1000. Okay, I guess that should be good. Then we can take a click here and move the graph to the side. Actually, we have to I cannot move it right now. Okay, now it has been somehow my keyboard doesn't work anymore. This works. This works. Okay, this works. Now it works again. Excuse me. Sorry. Okay. Well, it's not a clear. Well, it's a clear trend, but it's not really absolutely nice what we have here. But we have high damping for very low layers, but there the model was anyway bad. But even starting at 5 seconds here, where we have continuous layers, the damping is high, and then it goes down to low values. Actually, I would do the fit parameter pre-search, the grid fit, even a little bit more advanced by searching with several steps in 2 dimensions, and we will add this feature now. So we will go back to the list of fit parameters, and that's here. And actually, let's do grid fit also for the damping, so that we do a systematic scan. Let's do it with 20 points. And now we have to select an option in the options for fit parameters, because now we have 2 choices. Actually, we can do a sequence like this. First do this grid fit for the thickness, then use the best value and do the grid fit then for the damping. That would be 50 iterations here plus 20 here, 70 iterations. But it would not be a systematic scan of the full parameter space. That is obtained when for every of these 50 grid points, we try every 20 points here for the damping. So that would mean we have 1,000 iterations. Since the iterations are pretty quick, we can nevertheless do that. We can do 1,000. So in order to tell code which option we want, we have to go to File, Options, Fit, which gives us a dialog like this, which I will not explain in detail. I will only explain two things. First of all, for the grid fit, we have to activate multidimensional, and that's what we want for a systematic search. And then I would like to use here a time threshold when no fit parameter sets are used. This gives a limit, the overall limit for the fit, and we can put this to 10 seconds, which means that after 10 seconds the fit is stopped, even if it's not finished yet. But for a batch fit, we want to have a finite end, and usually it's a good idea to limit the length or the time period for one fit with an absolute end. Okay, that's all. Go to the batch control and now press go again, and now we will do a systematic two-dimensional parameter search, then with the best set of parameters do the downhill fitting, and then do it for all these 22 samples. Okay, press go. Here in the status bar you will see additional information about the progress of the grid fit for each sample. So and basically we will only see, we will not see updated models while the grid fit is done, only when the downhill simplex finds improved values. Okay, let's check if we can find better values, but probably the values are not really changing anymore. We found already the best ones before, where we did a little less systematic search, but now this is a nice example for a full search in the parameter space. Obviously, if you do this with 3, 4, or 5 parameters, or even more, you have to be very careful doing grid fits in many dimensions. So doing that in 3 or 4 dimensions means usually some hours of time to finish the search, and you have to plan that beforehand. But nevertheless, for some problems, in particular for design problems, you can use this multidimensional search in order to be sure that you really found the best solution. And okay, now the fitting is done. We have here a nice graph of the obtained damping constants, the thickness versus sputtering time, and the fit deviation versus sputtering time, which gives us a nice overview on all the results that we have achieved. Okay, I hope this was a good example explaining the feature batch fit control of code, and I hope that you will use it to do real systematic work for your case where you vary systematically, let's say, a magnetic field, a temperature, or whatever takes some influence on your layer properties. Thanks a lot for listening.